Hey everyone, in this video we're actually talking about mass again, which might sound weird, but now that we've learned about both Newton's second law and this force due to gravity, it's worth revisiting. There's almost a quirky little attribute about mass as we've been learning. So first, let's just do a quick little reminder. When we were learning about Newton's second law, here it is right here. This is just another version of this. The sum of the forces is equal to ma. Well, we had this m term, this term known as mass. We talked about how mass and inertia are very similar things, that mass is kind of how you measure the amount of inertia or the amount of laziness. M here you would call the inertial mass. It's how much laziness some object has, and an object accelerates based on that amount of total force and this amount of inertia, or this amount of inertial mass. That's what determines how much things accelerate. Okay, all right, we've done this. This is just review. Well, in the last couple of videos, we've been using this force due to gravity equation. And for this force due to gravity equation, oh my gosh, we learned that it's based on g, some constant. It's based on the distance between objects. It's also on these two masses. Remember, we said that this law, or this force, I should say, comes up because two masses attract to each other. There's a force between objects with mass. We say that this is gravitational mass. This is what feels a force between objects. It's based on the object's gravitational mass. The attractive force on matter is based on the distance between the objects and their inertia and their mass. Okay? Well, fine. Maybe you're curious about why I'm even rehashing all this stuff. This is the point. This is why we're talking about this in this video. These two equations, I've rewritten them right here. They are not, I'll repeat, they are not based on one another. You do not derive this equation from the second law, or vice versa. We've seen plenty of problems where we, maybe come up with the equation for impulse or kinetic energy by using or somehow rearranging Newton's second law, in some way, some form. These two equations are fully independent on one another. Both of them have mass in them, but you don't get one equation from the other. And in addition, every experiment and every observation we have ever done has always shown that these two masses, the mass right here and the masses right here, they are the same, okay? But here's the kicker. There's no reason why they are the same. There is no physical law, there is no pillar in physics or any other science that says the amount of mass that affects an object's acceleration, that's the same mass that attracts another thing in this object or this force we call gravity. These two things could be totally separate types of mass, okay? But they're not. Not only are they the same in our equations, but every time we do an observation, they always end up being the same value. Okay. Now, fine, maybe you feel that's a little quirky, but who the heck cares? This, in turn, actually is very important for a guy named Einstein. We're not actually going to get into Einstein's relativity theories, but if you're even just a little bit familiar with Einstein, you know he was a very famous physicist. One of his most famous physics theories ever was something known as his general theory of relativity. That whole theory, it starts with the preamble. The entire theory is based upon something called the equivalence principle, where Einstein is saying, let's have that inertial mass just be the exact same thing as that gravitational mass. And it seems reasonable, as I saw on the last slide, as I showed you on the last slide, every experiment always shows that these two things are equal. But there's no reason they have to be equal. His entire theory of general relativity, in fact, can only work in any way that we know it today, can only be functional if those two masses are, in fact, the same thing. Which begs the question, what if they're not the same thing? Again, every experiment we've done shows that they are. They could be used interchangeably. But what if maybe on the very tiny scale, the quantum scale, they are ever so slightly different? Einstein and his most famous theory would break down. What if this mass is actually different in the largest of scales, galaxies or clusters of galaxies? If that's true, again, one of his most famous theories, Einstein's reputation, would all of a sudden take a big hit because it's based on assuming they're the same. And this is interesting. This is, in fact, a branch of modern physics. This isn't something where we're just like, well, okay, they're the same, let's move on. We're trying to find out as scientists, as physicists, if these are in fact true, there are tests, modern tests going on to see whether this equivalence principle, if this thing that we've been using for Newton's second law and inertia, is really the same as the thing that we use every time we punch out that gravitational force equation. Here's just a couple of headlines I picked out. Stanford, I know this headline is a little old if you check out the date, but this is an ongoing experiment. Modern physics and top-tier universities are trying to test different things, looking at the acceleration that things fall to try and match whether or not these masses are in fact equal and or how small is this difference. Now, how it relates to us. Oh my gosh. Sorry, I had to hit pause and move my head to get it out of the way for a little bit. Time after time, in the last couple of videos even, we've been sensing, or we've been, I guess, just assuming that these masses have been the same. So, for example, when we set up Newton's second law using the force of gravity, what did we do? We canceled out the mass. That was assuming these masses are the same. And that's okay. I'm not saying you can't or you shouldn't do this, but just notice, it's a big assumption. It's worth noting that there's no actual reason that says they need to be the same, but it's something we do all the time. Don't stop doing it for the AP Physics 1 exam, but College Board, the current AP Physics 1 exam, might have questions asking about or referencing the inertial mass and or the gravitational mass. How do you know? Well, you kind of got to read the problem carefully. If it's talking about an experiment, well, I don't know, maybe you're applying a force, you are measuring the acceleration, and then you're using this equation to calculate m, that is you using inertia and Newton's second law. That's inertial mass. If it's an experiment where maybe you have two different masses, you are measuring the distance between them, and you are very carefully measuring the force between them. Oh, you're talking about the gravitational mass. So it's a situation where we've been kind of taking advantage of the fact that these two things seem like they're equal. We keep canceling them out, and you can keep doing that. But technically, you don't necessarily have to. There's no physical law that says they must. And you might see specific questions where they're asking you to identify which of these two masses you're actually utilizing and whether or not you can assume they're the same. In this class, we can, and we've always been assuming they are the same. But there's some nuance, and it actually gets into some modern physics and some modern cosmology. Einstein, general relativity, understanding the cosmos. In fact, I'll just tease you, we're not going to get into general relativity. There's an idea that, maybe the force of gravity, this whole thing, isn't really a force at all. Maybe it's just what happens when masses are accelerating. Maybe it's just a version of acceleration, like if you were in a rocket ship and it was accelerating, you would get the same kind of result. That is actually what relativity starts diving into, and it shows some pretty significant repercussions if you take that path. So if you're interested in relativity, you're going to have to look it up on your own, but it is worthwhile mentioning there are technically two different masses we've been utilizing. That's it. That's what I wanted to go over in this video. Thanks a lot for watching.